Welcome to Abstract Algebra 2. We're now in the topic Kernel, Image, and Isomorphism Theorems. Again, I'm Dr. Lois Adewoye Ademola. Okay, so we'll be considering homomorphic image, kernel, and image of a homomorphism, the first and second isomorphism. So we begin with the definitions and we'll state a lemma and we'll prove it. The first definition is what is the kernel of theta. So the kernel of theta is denoted theta, and it's simply all the elements in G, or collection of all elements G in G, such that the element, when theta takes it, it is mapped to the identity 1. So everything mapped to 1 is collected, and that is what we call the kernel. So the kernel collects everything mapped to the identity. Okay. Now, while the image of theta, denoted im theta, it collects all the images, that's g theta, as you can see there, for all the g's, small letter g in the group G itself. So that's the definition that you need to know. Lemma 1.12 in the lecture notes says let theta map G into G prime, and it's a homomorphism. I believe you know what a homomorphism is, you recall. It's the map that satisfies the condition that if you have AB theta, it's going to be equal to A theta, B theta, right? A theta, B theta. Okay, that's what our homomorphism is. Okay, so we have theta to be a homomorphism, so it satisfies that condition. We now said that once we have that, then the kernel is a normal subgroup of G, and it says also that the image theta is a subgroup of G prime. So we need to show that the kernel of theta is a normal subgroup of G. I put this just to show that it's a subgroup and it's also normal. Okay, and we also to show that the image of theta is a subgroup of G prime. Okay, so we'll prove in this video only the first part, that is that the kernel is normal in G. That's what we're going to show. Okay, so let's see. So we seek to show that the kernel of theta is normal in G. To do that, we need to show that the following holds. So first you can see that the kernel of theta must be a subgroup of G. That's what we want to show. And next we want to show is finally that the kernel of theta is normal in G, because it can't be normal unless it is a subgroup. Okay, so what is the identities we need to show for something to be normal in to be a subgroup? Remember, there are 3 identities you need to prove. You need to show that that thing is not empty, and that thing in particular for us is the kernel of theta. And if it is not empty, we can find 2 elements, say x, comma y, in the kernel of theta, right? Such that this will hold. That is, you can find to prove that y inverse lies in kernel of theta. The next one is that kernel xy inverse lies in kernel of theta. Once these 3 conditions hold, we say that the kernel of theta is a subgroup of G. But our target is to show that it is normal. So if it is normal, we say that the left coset, right, equals to the right coset, right? But in our case, H is the kernel of theta, right? And another way, if you recall the definition in the very first video, is that if you simply just show that G inverse KG lies in the kernel of theta, as you can see here, where K is in the kernel of theta and G is in G. Okay, so we just showed this 4 identities, and once these 4 identities are proven, we would have shown that the kernel of theta is actually normal in G. Okay, so let's move on. So we want to prove the first one. We want to show that the kernel of theta is not empty. If you recall in your very first video, we showed that 1 theta equal to 1. If you remember, where we use the identities, I think it's A times 1 equal to A. We use that for the proof. So now, if this is the case, it means that 1 lies in the kernel, right? Because the kernel, by definition, states that everything that it takes is taken to the identity 1, right? So if that is the case, we already know this is true. So that's why I said now 1 theta is equal to 1, which implies that 1 lies in the kernel of theta because of the definition of kernel of theta, which means that once there's 1 in the kernel of theta is not empty, right? So we're through with the first proof of 1. So we've succeeded in proving 1. We just need to prove this 2. Now that it's not empty, I'm free to pick any 2 elements of my choice. So in our case, we want to prove that. So since it's not empty, it follows that there exist x and y in the kernel of theta. So we pick 2 elements. And if this x and y are in the kernel of theta, what does the kernel of theta do? It takes any element. So if I take x, it will take it to 1, right? What of y? Definitely it will take y to 1 because they both lie in the kernel of theta. So that's how I was able to write my next line here. The next line says that since there exists x and y, then such that this condition will hold, which I called asterisk. Okay, so the next thing we need to prove again is to show that y inverse theta would be in the identity, would be in the kernel of theta. So now we know that y is in the kernel of theta. So what will happen to y inverse theta? Y inverse theta is same as this. How do I know that? Remember, we had shown in the previous videos that x all inverse is the same as x inverse theta. If you recall, you did that in the very first video, okay? So that is why I could say that, okay? So I know that y inverse theta is same as this. But you know what y theta is? See it here. It's 1. So because y theta is 1, I've put 1 here. And 1, I put 1 right here. And 1 all raised to power, the inverse is just simply 1 itself. And so it means that y inverse theta is equal to 1, which means that y inverse lies in the kernel of theta. Okay, so that's how I say hence y inverse lies in kernel of theta for all y in the kernel of theta, and that proves the second identity. Okay, so we've proven the second identity. We need to prove the third one. Okay, so let's prove the third one. For the third one, we know that x and y lies in this because in the kernel of theta because it's not empty, right? So what will x, y inverse theta look like? Because theta is a homomorphism, remember? It can split into this 2 because it's a homomorphism. Okay, but we know x theta, and you also know y inverse theta. You just proved y inverse theta lies in the kernel. So they're both 1, 1, right? And since they're both 1, 1, 1 times 1 is just 1. Wow. It means that x, y inverse theta is equal to 1. What does that mean? It means this element lies in the kernel of theta for all x and y. And so we've proved the third identity. So proving the third identity, let's go back. We've proved the third, right? Now we're proving the fourth one. We want to show finally that it is actually a normal subgroup. So let's see what to do. Okay. So with the third identity, the first identity, the first condition, second and third condition means that the kernel of theta is a subgroup, right, of theta. So we've succeeded in proving that. The next thing is this fourth one, which is to show that these elements lie in the kernel of theta. Okay, so let's see how it goes. So for all k in the kernel of theta and for all g, if we map this element, the theta map works on it. Because it's a homomorphism, it breaks it this way. You can see? It breaks it into 3 different, the theta splits it into 3, right? Okay, so this and this and this, right? But you know what this is? This one here. K is from the kernel. If k is from the kernel, it means that k theta is equal to 1, right? So that's the one, this k disappeared in the middle here because the kernel of theta means k theta is equal to 1. So you're left with this. Now, I couldn't have said g inverse theta is equal to 1. Neither can I say g theta is equal to 1 because g is not in the kernel of theta, but it is in g. But then, you know what g inverse theta is? It is g theta all inverse from that identity we had proven. And so g theta comes down as g theta. So what is this? G theta all inverse times g theta. That's just 1, right? So that's how we're able to get the value 1 there. Oh, what does that mean? This means that g inverse kernel of g, when theta acts on it, is equal to 1. So if this is equal to 1, it means that this thing lies in the kernel of theta for all k in the kernel of theta and for all g. And so we proved the fourth condition. So we proved the fourth condition, we proved the first, second, and third. And so the statement that the kernel of theta is a normal subgroup holds, and that is all through the proof of that theorem. Okay, the next things you need to know by heart, you just need to be able to state them. The first isomorphism theorem and the second isomorphism theorem. So all I need you to know is to be able to state them, that theta maps, if theta maps G into G prime, is a homomorphism of the groups, then G modulo the kernel of theta is isomorphic. So that's all you need to know, and thank you.